Good morning. My name is MD Hawk. Today I'm going to talk about microstrip patch antenna for my design project for electromagnetic field theory. First of all, let's talk about the antenna. Antenna is one of the most vital part of the wireless communication system, as all of we know. Therefore, to improve the wireless communication system, we must develop the high performance, low cost antenna. Microstrip patch antenna is one of the widely used antenna design in modern technology. Microstrip patch antenna consists of a radiating patch of on the side of a dielectric substrate which has a ground plane on the other side. The objective of this project is to design a rectangular microstrip patch antenna at 10 gigahertz on a 31 mil Roger R04350 board and study the effect of antenna dimension, length, width, substrate parameters, relative dielectric constant, substrate thickness, and radiation pattern. And I used HFSS 18.1 version, high frequency structure simulation to design patch antenna. So in this design, here are the parameters that we used to design the patch antenna, which is length, width, thickness, height of the substance, and the patch antenna, and also the input impedance of the transmission line, resonant frequency of the antenna, relative permeability of the substance, and dielectric loss tangent. The equations we used for these designs are following, where we calculate the width and dielectric constant and the actual length. Here is the complete, at a glance, here is the complete version of my design for patch antenna using HFSS. And as you can see, on the right side shows the E pattern patch antenna, and here is the complete version, and I assigned all the parameters that shows on the right side, and the value of the parameter shows on the left side that I used for this patch antenna, where the millimeter or the substrate is 40, the H of the H of the substrate is 31, the length of the patch antenna 4.5, weight is 10, and so on. These are the parameters I used to design the design. So first I use the substrate, where I use the Rogers of R04350. That's the model I used, and I assigned the value of the substance, where it says 40 millimeter and the height shows the 30 mil. And then on the substrate, I assign the value the ground plane, that I had to create another rectangular box and on top of the substrate, and then I assign those value on the ground plane. Then on the substrate I created the actual patch antenna, where I assigned those value, where the length is 7.5 millimeter and width is 10 millimeter. And now I created a gap on the patch antenna. The value of the gap is 2.6, 2.8 millimeter, x and y respectively. And the reason for the gap on the patch antenna is so we can feed the transmission line to the antenna. So here is the transmission line, transmission feed line for the antenna parameters, which is XOS value. And then what I did is I combined the feed line. I defined this as a feed line and the patch antenna inside the gap, and then I combined all together, so it matches, that become a E pattern patch antenna. Then top of the feed line I created a sources, the rectangular shape, that is for source, and the parameters also shows for the source is x and y's value 1.76 and 31 mil. So now I created a earbox on all over the patch antenna, so that we can simulate the radiation from the patch antenna, that's the electric current is coming from through the transmission line, and create the radiation that we can simulate that. So we create the earbox for that, and here is the dimension of the earbox, is right there. And then right before we simulate, we had to assign the sources for excitation, and for the ground and patch, E patch for boundary. The way we did it, we didn't do not much. It's kind of easy. We just right click on the ground plane and the E patch, and we just change the name that shows in there, and then we clicked on OK. Next, what we did is right before the simulation, we did the simulation setup, where we put the time, we put the gigahertz for 10 gigahertz, and we also did the frequency. We had the frequency show up before the simulation, final simulation. And here is the radiation setup on the left side, that shows the 3D parameters, and pretty much I didn't have to do nothing. I just it was all the numbers 360, 160. It was actually the parameters of 3D. So I just clicked on OK, and before the final run, I clicked on the validation check. So make sure all my parameters and all the it was assigned correctly. So it checked OK. It checked everything: design setting, 3D, boundary excitation, analysis setup, radiation. So everything was OK. So now I clicked it on the run button right there. It shows next to the check validation. and when I ran it, it took about 5 minutes to run it, and here is the final results that that we are expecting is for 10 gigahertz, that the frequency response that we found on the results, under the results S11, that's reflection coefficient, and the gain we had for 10 gigahertz was minus 18 dB, and 3D, the radiation pattern it shows on the bottom is a very nice gain. It shows that has little over 6.6 little over 6 giga dB gain for this patch antenna, and couple of lobes are shows on the bottom, but overall the gain was very good for 10 gigahertz, which is little over 6 dB, which is typically which is typical for patch antenna, like 6 to 7 dB, so which is not bad. So we have a little over 6. So the conclusion, the rectangular microstrip antenna was designed and analyzed with the frequency range of 10 gigahertz and simulated by using HFSS 18.1 software. The frequency response and the 3D simulation pattern are obtained, and the gain of the microstrip patch antenna, as I just mentioned earlier, which was a little over 6 dB, and the radiation pattern is minus 18 dB for 10 gigahertz frequency. And here are the references, and thank you for your time.